In this lecture, we look at standing waves. Standing waves occur when two counterpropagating waves superpose. Here we have a blue curve and a red curve, which are counterpropagating. Those two waves produce the sum, the black curve, which is a standing wave which just goes up and down but does not propagate. If we write this down algebraically, we have that y of x and t is equal to a sinusoid with an amplitude of a, kx minus omega t, which gives us a wave propagating to the right, plus the amplitude times the sine of kx plus omega t, which gives us the red wave propagating to the left. If we use a trig identity on this formula, we find that this identity is that sine of alpha plus sine of beta is equal to 2 times the cosine of 1/2 the difference between alpha and beta times sine of 1/2 the sum of alpha and beta. So that we have y of x and t is equal to 2 times the amplitude of sine of kx cosine of minus omega t. At some fixed position x, if we look at one point of x, we see that the amplitude will oscillate, given by this cosine of minus omega t. There are certain points called nodes that if sine of kx is equal to 0, then y is equal to 0 for all time. That implies that k times x is equal to 0 or some integer multiple of pi, so that x is equal to n times lambda over 2. So if we take a look at where this occurs, we put one line where there's a node for the black curve, and we see it starts there. So you see so that there is no amplitude on the black curve at that point. We put a second one in to the next node, and the spacing between the two green dotted lines is lambda over 2, or half the wavelength. Antinodes, where you have the maximum amplitude, occur if sine of kx is equal to 1. So the maximum amplitude occurs when kx is equal to m plus 1 times pi over 2, or x is equal to m plus 1/2 times lambda over 2. And if we look at the dotted red curve, we see that spacing between them also is lambda over 2. Let's take a look at an example with a guitar string. Here we have a string stretched between two anchoring points. The vibration of a guitar string produces a musical note. How does pressing on the guitar string change the note? The length of our string is 1 meter. When you pluck the guitar string, it vibrates in a standing wave. There are nodes at each end, so it can't be a propagating wave. And the frequency of the sound is f is equal to the square root of the tension divided by the mass per unit length. This is how tightly you turn the screw on your guitar and how heavy the string is per unit length. Both of those things are rather fixed. You can't change. It's not so easy to turn the knob while you're playing, and the mass per unit length is fixed by the string. The distance between the nodes is lambda over 2 for a standing wave. So this is equal to L, or 1 meter. So F is equal to the square root of T over mu divided by 2L. And a reasonable number for the square root of T over mu is about 200 meters per second. Divided by 2 meters gives us an answer of 100 hertz. We change the frequency or note by placing a finger in the center of the string. So we put our finger there in the center of the string, and then what happens is we have another node there. By adding another node at the center, then the spacing between nodes is still lambda over 2, but now that lambda over 2 is equal to L divided by 2. So lambda is equal to L is equal to 1 meter. So F is equal to the same top, 200 meters per second, divided by 1 meter. So it's now equal to 200 hertz. So by putting your finger in the center of the string, you double the frequency.